8, lecture 41. So yesterday we saw that you can model any modulator in this manner. This is X, this is Y, this is V, and this transfer function is L0, this transfer function is L1. What we did see was the signal here is approximately X plus NTF of Z minus 1 times E of Z. I mean, this is assuming that X is a low frequency signal, and in the when the input frequency is very, very low, we know that the signal transfer function is almost equal to 1, which means that the input to the quantizer must have approximately X. On top of it is riding quantization noise, which has been shaped by a filter with an impulse response NTF of Z minus 1. I mean, we also saw yesterday that the variance of the noise at the input to the quantizer, okay, because this noise, the basic quantization noise which we have treated as additive, has gone propagated through the loop. So the variance of the noise at the input of the quantizer is certainly not delta square by 12, but a large multiple of delta square by 12. And this large multiple starts to get larger and larger the moment the order starts to get higher. Okay. So for example, so variance of the noise at the quantizer input is nothing but sigma Hn h of k whole square minus 1 for 1 minus z inverse the whole square. It is how much? 1 minus 2 1, so 5 times delta square by 12. For 1 minus z inverse the whole cube, it will be 9 delta square by 12, 19, yeah, sorry. And for 1 minus z inverse whole to the power 4, what do you see? 1 2 1 1 3 3 1 1 4 6 4 1, and so what is it now? 69. Clearly you can see that as the order goes on increasing, and why were we interested in increasing the order of the noise transfer function? We were very excited by the fact that by going on increasing the order, the in-band quantization noise can be dramatically reduced. But then now we see that as the in-band quantization noise is reduced, the gain of the noise transfer function at out-of-band frequencies, okay, goes on increasing from what was originally 4 to 8 to 16. 1 minus z inverse whole to the power 4, it is 16. Okay. Modeling our saturating quantizer by a linear approximation, we saw the following, which is if the noise waveform variance increases, then what do you think will happen to the probability that the quantizer will clip? Increases or decreases? Increases, right? So if noise variance at y increases, probability of clipping or overload increases, which means what? The probability of, I mean, if the saturator, if the quantizer saturates or overloads more often, what can you say about the average gain of the quantizer for the noise-like signal? So gain for the noise decreases, which means the poles will move closer to the unit circle, and eventually this will become, the modulator becomes unstable. So this is all background information that you know already. Let's try and figure out, what all trade-offs there are. The first thing, of course, is that the maximum stable amplitude, okay, which at this point we will simply define to be the maximum DC input you can put into the modulator before the loop becomes unstable, okay, has to be definitely smaller than the full scale of the quantizer. Because, intuitively speaking, we know that the average of the output, the output has to be filtered by a sharp digital filter to get the true representation of the input. And what is filtering? Filtering is nothing but is clever averaging, that's all. So, the average value of the output bit stream or the output quantization levels is equal to the input. So, if the average of some quantity is equal to the input, it must follow that that quantity which is being averaged must at some times be larger than the input and sometimes be smaller. And the key to preventing instability in the modulator is simply to avoid quantizer overload. Right? As long as everything is within that step-like staircase region, everything is fine. The moment you start to hit levels where the output of the quantizer becomes clipped, that's when you have trouble. The maximum stable amplitude of the modulator is definitely less than full scale. Where full scale is defined as, this is the so-called average slope, right, which is 1. Up to where do you think the quantizer is not overloaded? The range of the quantizer is around. For stable operation, the input signals cannot go all the way from this point to this point. They can only occupy a range like this. Now, let's figure out intuitively, let's try to understand what happens to the maximum stable amplitude as, different properties of the loop change. For example, as for an NTF of the form 1 minus Z inverse whole to the power n, if n increases, what can you say about the MSA? Decreases. Why? Amplification of the quantization noise through the loop is much more as the NTF order increases. The next thing, what about the number of quantization levels? Let's say we had the same full scale, right? So let me call this minus Vref by 2 to Vref by 2, so that the quantizer full scale is Vref, alright? If I divided this full scale into a larger number of bins, right, instead of having how many levels here? 1, 2, 3, 4, 5, 6. If I double the number of levels, what do you think will happen to the MSA? Okay, so as the number of levels increase, the maximum stable amplitude will decrease or increase? It should increase. Why should it increase? So, if you take the same full scale range and have more levels within that full scale range, what is happening? The LSD size is decreasing. Even though the noise transfer function remains the same, the amplification factor with which the quantization noise gets amplified will remain the same. However, the amplitude of the noise has gone down by a factor of 2 if I double the number of levels, because the quantization noise has gone down, which means that I can push up my input closer to the full scale before the quantizer will saturate. And by the same logic, if I have a coarser quantizer, in other words, if the number of quantizer levels within the full scale decrease, then the maximum stable amplitude will fall down. So, the fundamental problem with having noise transfer functions of the form 1 minus Z inverse to the power n, where n is a large number, say 4 or 3 or whatever, is the problem of quantizer overload. And what do you think is the easiest kind of quantizer to implement? The 1-bit quantizer. So we all started off with this quantizer with many levels, and then we said that we are able to push the quantization noise outside the signal band. So it follows that you get very greedy and say, okay, if I can use a sloppy quantizer, I'll use the sloppiest quantizer I can possibly think of, which is nothing but a 1-bit quantizer. So the output levels, instead of being like this, will be something like this. So you can see clearly that the 1-bit quantizer has got huge quantization error variance, because what was earlier divided into so many levels is just one single level. The output of the modulator will run between either 1 or 0, or minus Vref and plus Vref with no intermediate levels at all. And it turns out that single bit modulators are very much used today. And the reason why you use a single bit modulator is simply because of the simplicity of implementing the quantizer itself. And you hope that this noise shaping will remove all the quantization noise anyway from the signal bank. But as you can imagine, as the number of levels becomes smaller and smaller, what do you think will happen to the maximum stable amplitude? It will decrease dramatically. So single bit modulators, which are actually very commonly used, have very, very small maximum stable amplitudes if the order is increased. Now, so this problem has to be fixed, because you do not want the maximum stable amplitude to be, if your full scale is Vref, it doesn't make any sense for the maximum stable amplitude of your modulator to be only 0.1 Vref. So you want in principle to be able to use a reasonable, you know that expecting Vref is foolish, but you would want to be able to use maybe at least 70 to 80% of the full scale. So the question is, what do you do? So to figure out what the solution is, you must know what the problem is, and the problem we all know to be the following, which is, as the order goes on increasing, the problem is this guy. The variance of the noise at the input to the quantizer is simply increasing because of the high frequency gain of the noise transfer function. We like this part, but we do not like this part. What do you think we can do? So you don't choose a noise. This noise transfer function is of the form 1 minus z inverse whole to the power n, which is of the form. Let me take an example of say for fourth order, z minus 1 to the power 4 by z to the power 4. This is nothing but 1 minus z inverse whole to the power 4. And the problem with this is that the out of band gain is 16. What we want is, we want the noise shaping at low frequency. However, we do not want this high gain at high frequencies. So one idea that I can think of is to say, if you multiplied the noise transfer function by another transfer function of this form, what do you think will happen? The out of band gain will decrease, the in band shape will look, as long as this is fairly constant here, okay, if you multiply 0 by a constant, it is still 0. So the in band performance will remain the same. Hopefully, we'll see that that's not entirely true, but clearly the out of band gain is reducing, which means that the variance of the noise at the input of the quantizer will reduce, which means that the stability of the modulator will be enhanced. In other words, overload now happens a lot less frequently, which means that the gain of the quantizer falling off also gets delayed, which means that you can put in larger input signals before the quantizer overloads and causes the whole modulator to become unstable. If you do not want to increase the order, how do I, before I get there, where are the poles of the NTF? All the poles are at 0. 1, 2, 3, 4. Okay. All the zeros are at z equal to 1. So there are 4 of these guys and there are 4 of these guys. How will I be able to multiply, how will I be able to get this extra guy? This is nothing but a digital low pass filter. How do I get a digital low pass filter? What do you think the pole zero constellation of a low pass filter should be? If I had an all pole low pass filter, digital low pass filter, where do you think the poles must be? Okay, let me get back to continuous time and then we go to discrete time. This is the S plane. want to pass only frequencies around here. So where should the poles be? If you put poles here, if you keep traveling along the j omega axis like this, what is the magnitude of the response at a certain j omega? It is basically the distance for 1 over the distance. If this is P1 and this is P2 and this is whatever P3 and P4, mod h of j omega is nothing but 1 over mod P1, P2, P3, P4 and so on. So when you are close to the origin, the vectors drawn from the origin to j omega are all small in length. So the magnitude response there is high. As you keep going progressively away from DC, you see that the length of these poles becomes longer and longer, thereby causing the magnitude response to droop. And as I was mentioning yesterday, to convert the S-plane, to convert your intuition from the S-plane into the Z-plane, all that you do is basically take this j omega axis which was like this and then simply convert it into a circle, right? Because the bilinear transform, all that it does is convert straight lines and circles into straight lines and circles. Correct? And basically all that you need to say is circles get converted, it's a conformal map. So circles become circles, and a nice way of looking at a straight line is think of it as a infinitely large circle. So all that the bilinear transform is doing is taking the j omega axis and converting it into the unit circle, thereby pushing all the stuff in the left half S plane to within the unit circle. So if you want a low pass sigma delta modulator, if you want a low pass filter, what do you think the poles, where do you think the poles should be? Very good. So what you want is, you do not want these guys. What you want is these poles to move closer to DC. Where is DC? At z equal to 1. So you want to remove these poles and put them perhaps somewhere around here. The exact constellation we'll figure out a little later, but the general idea is to be able to move the poles close to z equal to 1. So if I just added extra poles at z equal to 1, that will do the job. However, what will that do? It will also increase the order. So what I should do is not simply add extra poles at around z equal to 1. I must also eliminate the poles at z equal to 0. So in other words, I must modify the noise transfer function as z minus 1 whole to the 4 by z to the power 4. I want to remove the 4 poles at the origin. So I will multiply by z to the power 4, and I will add a denominator polynomial of the form z power 4 plus ak z to the k equal to 1 to 0 to 0. Thank you. So this goes away, and you are now left with a pole zero constellation of this form. You can equivalently think of moving all the poles from the origin to somewhere close to the z equal to 1 point. So in other words, multiply the numerator and denominator by z inverse whole to the power 4, then I will get a modified noise transfer function of the form 1 minus z inverse whole to the power 4 divided by a naught plus a1 z inverse plus a2 z to the minus 2 blah 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 plus a4 z to the minus. The earlier case we had 1 minus z inverse whole to the power 4 by 1. Alright, the denominator was simply a constant. Now you have a denominator which is a polynomial, and the coefficients of the polynomial have to be chosen intelligently, making sure that the poles of the roots of the denominator lie close to somewhere around here. And poles here basically means that the value, the gain at z equal to at omega equal to pi, which is z equal to minus 1, is inversely proportional to these vectors. So you can see that due to the placement of these poles, the gain at z equal to 1 is definitely smaller than the gain at z equal to 0. And you want the position, these extra poles to form a low pass type function because you want to filter off the high frequency part of the quantization noise, which means that the gain at 0 must be larger than, you want something like this. So the gain at omega equal to 0, which is z equal to 1, must be larger than the gain at omega equal to pi or z equal to minus 1, and clearly that is the case if the poles are pushed towards z equal to 1, as you can simply convince yourself by drawing those vectors. Okay, the question is why not, why did you choose a fourth order polynomial, why not a fifth order polynomial? Yes, okay. Yeah, the minimum you need is 4, sure. But is there anything preventing you from using 5? The number of poles must be the same as the number of zeros, right? So if I had a fifth order denominator, I might have as well gone for 1 minus z inverse whole to the power 5. So the number of poles and the number of zeros must be equal. So instead of wasting 1 0 and making it somewhere else, I might as well make use of all the zeros and use the minimum number of poles. But there is nothing wrong in using a fourth order numerator 1 minus z inverse whole to the power 4 and a fifth order denominator. In many practical situations it turns out that indeed becomes the case because of non-idealities in the realization. But at this point, purely from a theory point of view, there is nothing preventing you from doing it. However, this is the canonical thing, right? So this is the transfer function which will give you the lowest order transfer function which will give you 4 zeros at the order at z equal to 1 and a low pass type. And all the trick is in the denominator. By making a poor choice of A0, A1, etc. through A4, you can screw up big time, right? If you, instead of choosing the poles close to the origin, if you went and chose the poles at close to pi, then it's a double whammy, right? What would have been 16 will now become 60. And that's very easily possible if you just, if you mistake the order of A0 to A4, and if you make A4 equal to A0 and if you just transpose the matrix, you will get something where the outer band gain goes to a very, very large value. Yes, very good. So, the next point that I want to make is the following: are there any particular constraints that you can identify in the NTF right away? What did we discuss? The impulse response, the first term of the impulse response of an NTF must be 1, which is equivalent to saying that the NTF of z evaluated at z equal to infinity must be 1. So now can you tell me any condition on the denominator? A0 must be equal to 1. Because h of 0, which must be NTF evaluated at z equal to infinity, must be 1. So it now boils down to choosing 4 numbers in this particular fourth order example. Then the next quarrel is, okay, my original NTF was like this, and now I am trying to do something like this. This reduces the outer band gain, so does this, so does this, so does this. So the question now is, there are a bazillion ways of generating a low pass filter, fourth order low pass filter, which will attenuate high frequency components. The question is, what do I use? And the answer is, is more a practical one. So what people do is recognize the fact that a lot of work has been done. People have really beaten to death IIR filter design. This is nothing but an IIR filter, right? So 1 minus z inverse whole power 4 in this particular example by d of z, okay, d of z inverse is nothing but a high pass filter. And there are, many families of high pass filters, and people have gone and, figured out ways of computing the coefficients of high pass filters given, pass band ripple, and see, this approximation problem has been solved. Given, if you want to approximate this brick wall characteristic, This has got nothing to do with sigma delta modulators, right? So this is nothing but a high pass filter design problem. So you want to you want to reject low frequencies, you want to accept high frequencies. So the ideal transfer function you are trying to realize for a high pass filter is a brick wall of this form. Clearly, a finite order system will never be able to, a physically realizable system will never be able to implement this infinite slope in the frequency domain. So there are only ways of approximating this characteristic by various methods. And one of them is the so-called, how do you do it? I mean, you've all done ADSP or whatever, right? So given a filter spec in the digital domain, how will you use your infinite wisdom and figure out the answer? The easiest thing, of course, is to, so what does the textbook say? Textbook says that, people have figured out, I mean, those guys were also, kind of lazy folks, so they decided, hey, why, start figuring out everything out from scratch. The analog filter guys, they figured this all out, like, 100 years back. So we might as well, latch on to those guys and see if anything useful can be gleaned from all that work. This bilinear transform way of generating digital high pass filter, IIR filters from analog prototypes is a very, very well-known thing, right? So the analog high pass stuff is again a frequency transformation of the analog low pass filter. So all that people have spent a lot of time trying to approximate something, how to realize the characteristic of this form. Once you do that, you can go and fool around with the transfer functions and make, something look like, once you're given a low pass filter transfer function, you can make it, you can derive an equivalent high pass filter transfer function by what are called frequency transformations. At least you must know that given an analog filter transfer function, I will be able to use the bilinear transform and get a digital transform, digital filter with the same shape. The next best way is, of course, you go to MATLAB and say, I want a high pass filter with this order and this ripple, right? So that's precisely what MATLAB is nothing but coding known routines, right? So whatever people have discovered is probably there in MATLAB. One popular way of approximating this brick wall, there are many families. One is called the Butterworth response. So, alright, so if you go to MATLAB and say, I want a Butterworth filter with, it assumes a default gain of 1. If you say I want a Butterworth high pass filter with a certain omega 3 dB, which lies between 0 and pi, it will give you the coefficients. And it turns out that all the zeros of the Butterworth high pass filter all lie at the origin. So the transfer function will be of the form 1 minus z inverse whole to the power 4 divided by some a naught plus a1 z inverse plus blah blah blah. This just happens to be the transfer function of a fourth order Butterworth high pass filter, which is known because of work of lots of people before us. As you keep increasing the order and while keeping the same omega 3 dB, what do you think will happen to the response? It will become sharper and sharper. So if this is fourth order, this will be fifth order, and as the order goes on increasing, the sharpness of this roll-off will go on increasing. So, but the bottom line is that it is possible to, using MATLAB or any other numerical evaluation tool, to be able to figure out the transfer function of an nth order high pass filter with all zeros at the origin, or in the z domain, all the zeros at z equal to 1. And then we realize that, hey, why bother trying to figure out pole positions? We might as well start off with a Butterworth characteristic. If you start off with the Butterworth characteristic, what do you, so this is a fourth order high pass filter. Can this be a noise transfer function? See, our NTF is also a fourth order high pass filter. This is also a fourth order high pass filter. So the question is, can this be an NTF? Can this be realized physically? So when can a high pass filter transfer function be a practical NTF? Do you understand the question? We all realize that we want an NTF. I mean, our NTF is of this form. It has 4 zeros at z equal to 1 and a denominator polynomial. So in other words, this is nothing but a high pass filter because it's suppressing low frequencies and letting through high frequencies. And let's say we have a magic box which will give us transfer functions of a high pass filter given a cutoff frequency. So clearly this is also a high pass filter. So the question is, can we use this knowledge of the fact that this is a high pass filter and conclude that this is an NTF? NTF is high pass, this is also a high pass transfer function, so the two of them should be the same, right? So can't we just simply use this as our NTF? While it is certainly true that this is a high pass filter transfer function, right? To make it a realizable NTF or to be able to realize this transfer function shape as a noise transfer function, you must constrain A0 to be equal to 1. Okay, so what can you do to make A0 equal to 1? I simply multiply the numerator by A0. So this will make, as z tends to infinity, the numerator will become A0, the denominator will become A0. So NTF of z equal to infinity becomes 1. So which means that this can now be realized as an NTF, because the first sample of the impulse response of an NTF must be equal to 0. So another thing, that if I wanted to generate a physically realizable NTF, what I will do is find a high pass filter transfer function and multiply or scale it so that let me call this high pass transfer function h1 of z, such that c times h1 of z evaluated at infinity must be equal to 1. This is now a physically realizable noise transfer function. We will definitely do an example, right? But this is the basic idea. Once you get the NTF, the next thing is what? Once you have the NTF, you have to realize the NTF. So then, let's say, for simplicity, this is a special case of a delta sigma modulator loop. So what is the NTF of this loop? Given the loop filter transfer function is L of z, what are the STF and what is the NTF? STF is L by 1 plus L. What about the NTF? 1 by 1 plus L of z. So if you want to realize this NTF, so you know this, you have to find L of z. So for example, if the NTF was known to be 1 minus z inverse the whole square, this must be equal to 1 by 1 plus L of z, which means L of z must be of the form 1 by 1 minus z inverse the whole square minus 1, which is 1 minus 1 minus z inverse the whole square divided by 1 minus z inverse the whole square, which is 1 minus 1 minus z inverse times 1 plus 1 minus z inverse divided by 1 minus z inverse the whole square, z inverse times 1 by 1 minus z inverse plus 1 by 1 minus z inverse the This is just arithmetic, okay? And as you expect, at low frequencies, the gain of the loop filter must go as, okay, at low frequencies, how is the NTF going? It's going as omega 1 minus Z inverse whole square at low frequencies is going as omega square, which means that the gain of the loop filter at low frequencies must go as 1 by omega square. Correct? No. It's 1 by, the NTF is 1 by 1 plus L of, NTF at low frequencies is 1 by 1 plus the gain of the loop filter at low frequencies. At low frequencies, the gain of the loop filter is so large that 1 is negligible in comparison to L of j omega, which means that if the NTF of j omega increases as omega square, it must follow that L of j omega must go down as 1 over omega square. In general, if you have an nth order noise transfer function, the NTF at low frequencies will go as omega to the power n, whereas the loop filter gain at low frequencies will go as 1 over omega to the power n, which means that how many integrators do you need in the loop? You need n integrators in the loop. And as you can see here, there are definitely 2 integrators. Okay, so I'll stop here.